Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to determine if a subset of a vector space is itself a vector space, that is, a subspace of the larger vector space. So, in this topic, we will describe the idea of a subspace, that is, a subset of a vector space that is itself a vector space. We will consider a few examples, including, for example, subspaces of R2 and R3. We will prove a few theorems regarding such subspaces, and we will consider the subspace of all linear combinations of a finite set of vectors. Let's look at R2, and let's focus on a subset of R2 that contains just one vector, the zero vector. Notice that if we add any two vectors in S, well, there's only one vector in S, so if we add that vector to itself, we get back the zero vector because 0 plus 0 is equal to 0. Notice also that if we multiply any vector in S, well, again, S only has one vector, then that scalar multiple, once again, is the zero vector. Thus, this subset of just the zero vector is actually closed under vector addition and scalar multiplication. And if you consider all the rest of the axioms of vector spaces, you will see that while it's exceptionally boring, this one vector does actually satisfy all the axioms of a vector space. Now, any subset of a vector space that is closed under vector addition and scalar multiplication is said to be a subspace of the larger vector space. So, the subset containing just the zero vector is a vector space contained inside of R2. It's a subspace. Now, another subspace of R2 is all of R2. In fact, given any vector space V, we are going to call both the subset containing just the zero vector and all of V itself, we will call these the trivial subspaces of V. Now, the interesting question is, are there any other subsets of vector spaces that are themselves vector spaces? How about the empty set? The empty set is a subset of R2. It contains no vectors. Is that a subspace? Well, if you take a look at the axioms of a vector space, one of the requirements is that there is a zero vector. You must have a zero vector in order for a collection of objects you're calling vectors to actually be a vector space. Thus, the empty set not having a zero vector is not a subspace of R2 or any other subspace. So the smallest subspace of any vector space is the subset containing only the zero vector. Now, recall that two of the axioms of a vector space are that the vector space must be closed under scalar multiplication and vector addition. There's a whole bunch of other axioms, but we're going to focus on just the closure ones. So, a subset S of a vector space V is itself a vector space if the sum of any two vectors in S is itself again a vector in S. All scalar multiples of a vector in S are themselves vectors in S. Now, is that sufficient? Well, all the other axioms simply deal with the operations of scalar multiplication, vector addition, the existence of a zero vector, and the existence of additive inverses. But if these two conditions are true, then all the other conditions must also be true for all of the vectors in S. After all, the additive inverse of any vector can be found by multiplying that vector by -1. And since all scalar multiples of any vector in S are again in S anyway, you've shown that, then -1 times any vector must also be in S. Also, 0 times any vector in S must be in S, and 0 times any vector, we've already shown, is the zero vector. So, if we can show that any subset is closed under vector addition and scalar multiplication, S is a vector space, and because it is a subset of the vector space V, we will call it a subspace of the vector space V. Now, let's actually look at a vector space that you're already familiar with. However, you didn't know it was actually a vector space. Consider the vector space of all polynomials with real coefficients. Now, we've already shown that this is a vector space. If I add two polynomials together, I get a polynomial back. If I multiply a polynomial by a scalar, I get a polynomial back. There is the zero polynomial, and given any polynomial, multiplying it by -1 gives us its additive inverse. Now, consider the following subset S sub 5 defined to be all polynomials of degree less than or equal to 5. So x to the power 6 is not in this set. Now, if I start off with a polynomial of degree less than or equal to 5, and I multiply that by any scalar, the result must still be a polynomial of degree less than or equal to 5. I cannot multiply the polynomial x to the 5 by any scalar and get something that has an x to the 6 in it. Okay, so this subset of all polynomials is closed under scalar multiplication. Also, if I add two polynomials of degree less than or equal to 5, I can't end up with a polynomial of degree 7. It's just not possible. Adding two polynomials of degree less than or equal to 5 must result in a polynomial of degree less than or equal to 5. So, therefore, S sub 5 must be a vector space. If I'm only dealing with polynomials of degree less than or equal to 5, that must form a vector space, and that vector space is contained inside the vector space of all polynomials. Therefore, it is a subspace of the vector space of all polynomials with real coefficients in a single variable x. In R2, let's now begin by considering all scalar multiples of this vector u. Could be any vector, but we'll just pick this one. So all scalar multiples of u forms a line that passes through u and the origin. So there we have a subset of R2. Now, the vector 4, 2 is such a vector. After all, the vector v equaling 4, 2 is just twice the vector 2, 1. Therefore, v is equal to alpha times u for some alpha. Well, specifically alpha equaling 2. Now, what happens if v is an arbitrary multiple of u? So v is any point on that line. Well, if I now take that point on that line and multiply it by beta, notice that beta times v must therefore be beta times the vector alpha times u. But by the properties of associativity with field multiplication and scalar multiplication, we have that beta times v is the scalar multiple beta times alpha of u. So therefore, any scalar multiple of any point on that line is still on that line. Now, as another example, here v1 and v2 are two vectors that are on this line. So v1 here is 3 times u, whereas v2 is negative 0.5 times u. Also, if we add these two together, we get that the sum of these two vectors is the vector 5, 2.5, which is equal to, yet again, another scalar multiple of u. Thus, it seems the sum of these two vectors, which are on this line, continues to remain on this line. Well, rather than showing it just for R2, let's prove this in general. Theorem. If V is any vector space and U is any vector in this vector space, including possibly the zero vector, then the subset S of all scalar multiples of U is a subspace of V. Okay, so given any vector, we're just going to consider all scalar multiples of it. Proof. So if V is any vector in S, then V must be equal to beta times U for some beta, by definition. Therefore, alpha times this vector V is alpha times the vector beta times U, which is equal to alpha times beta times U. So therefore, because alpha beta is a scalar, therefore alpha beta times u is a scalar multiple of u, and therefore alpha beta times u is in the subset S. So therefore alpha times v is also in S. Now, if v1 and v2 are in this subset S, then v1 must be some scalar multiple of u, and v2 must be another scalar multiple of u, for some beta 1 and beta 2. I don't know what they are, but it doesn't matter. There must be such numbers. If I now add these two vectors v1 and v2 together, I'm actually just adding beta 1 times u plus beta 2 times u. But you will recall that scalar multiplication distributes over scalar addition. And therefore, the sum of these two vectors, v1 plus v2, is actually just the product of quantity beta 1 plus beta 2 all times the vector u. So therefore, if I add any two vectors that are scalar multiples of u, the result must still be a scalar multiple of u, and therefore S is closed under vector addition. So if S is closed under vector addition and scalar multiplication, it is a vector space, and because it is a subset of V, we will call it a subspace of V. Thus, any, quote, line through the origin, unquote, in a vector space is a subspace. Here's one example. In the vector space of all polynomials in X with real coefficients, note that x squared is a vector in this vector space. Therefore, all scalar multiples alpha times x squared also forms a subspace of all polynomials. If I have a vector space, a polynomial of the form alpha times x squared, and I multiply that by a scalar, it's still going to be a scalar times x squared. If I add 3 times x squared plus 5 times x squared, the result is 8 times x squared. So it's still going to be a scalar of x squared. So it doesn't matter what vector space you're in, the scalar multiples of any one vector does form a vector space. Now, what happens if a line does not pass through the origin? So for example, consider all vectors of the form 0, 1 plus all scalar multiples of the vector 2, 1. This sort of forms the line, the dotted line that you see in the image in the lower right. Now, one such point on that line is of course the vector 0, 1, because that vector is equal to 0, 1 plus 0 times the vector 2, 1. Notice, however, that twice that vector is not on that line. In fact, twice that vector is the vector that ends right there. And as we can see, that point is not on the line. Consequently, this line that does not pass through the origin is not a subspace of R2. It's a subset, but it's not a subspace. So that previous subset did not contain the zero vector. So what we're going to do is prove a much more general theorem. Given a vector space V, any subset S of V that does not contain the zero vector is not a subspace of the vector space V. Proof. Well, if S is the empty set, we've already shown that it is not a subspace because the empty set does not contain the zero vector. If S is not equal to the empty set, then S must have at least one vector. And because we assumed that S did not have the zero vector, this one vector U must not be the zero vector. Notice, however, that 0 times the vector U is the zero vector, and thus S is not closed under scalar multiplication, as we assumed that the set S did not have the zero vector. Therefore, any subset that does not contain the zero vector cannot be a subspace of a given vector space. Now, consider the set T of all non-negative scalar multiples of a given vector U. As the image shows, this forms a ray coming out of and including the origin. Now, if V1 and V2 are any two vectors on this ray, then there must be non-negative scalars alpha 1 and alpha 2 such that V1 is alpha 1 times U and V2 is alpha 2 times U. Therefore, if we add these two vectors together, the result is alpha 1 plus alpha 2 all times the vector U. But wait a second. Adding two non-negative real numbers must give a non-negative real number, and therefore the sum of V1 and V2 must continue to lie on this ray. Thus, this ray is actually closed under vector addition. However, notice that negative 1 times U is a vector that is in the fourth quadrant, and it is the additive inverse of U. This is a scalar multiple of U that is not in this ray. Consequently, the set T is not closed under scalar multiplication. Therefore, rays emanating out of the origin do not form a subspace of a given vector space. Now, the region in red, assumed of course to extend to infinity, forms a cone based at the origin. Is this region a subspace of R2? Well, interestingly enough, if we take any two vectors in this cone, that is in the red region, and add them together, the result must actually be still in the cone. Try it out sometime. However, if we multiply any vector in this cone by -1, apart from just the 0 vector, the product is not in the cone because the product appears on the left-hand side of the y-axis. So this cone is not closed under scalar multiplication. All right, so let's add all scalar multiples of those vectors that are already in this cone. This essentially gives us the following double cone. Is this a subspace? Well, it's definitely closed under scalar multiplication because any vector that is multiplied by a positive scalar remains in the cone it is in. Any vector in this double cone that is multiplied by 0 ends up at the origin, and any vector in either of these cones multiplied by a negative real number ends up in the other half. So it is closed under scalar multiplication. Is it closed under vector addition? Unfortunately not. Try adding the following two vectors. Now, I didn't explicitly define the lines here, but as you can see, the vector 1, 0.1 is clearly within the right-hand cone, and the vector -1, 0.1 going up is also definitely within the left-hand cone. However, the sum of these two vectors is the vector 0, 0.2. Well, that's the vector right there. And that vector that ends at that point is not in either of the two cones. Therefore, this double cone is not a vector space, and therefore it is not a subspace. What's interesting is, given any vector xy in R2, we can find that vector to be the sum of two vectors in this cone. Basically, all we have to do is find a large enough n so that n plus 1 times x remains in the cone and negative nx y remains in the cone. If negative nxy is too far above or outside the cone, we can just increase the value of n. However, the sum of these two vectors is indeed equal to the vector xy. Thus, the smallest subset that is also a vector space that contains this double cone is actually all of R2. Now, if you didn't get that, don't worry too much about it. But the point being is there is no subspace between a line going through the origin and all of R2. Thus, in general, you can actually show that all subspaces of R2 include the trivial subspace containing just the 0 vector, all lines, and I literally mean all lines, passing through the origin. Those form a vector space. And then there is the trivial R space of all of R2. So let's look at a little bit more general proof. Given any finite set of m vectors in some vector space V, the set S of all scalar multiples of these m vectors, that is, all vectors of the form alpha 1 times u1 plus alpha 2 times u2 plus all the way to alpha m times um, where we let alpha 1, alpha 2, and all the way up to alpha m be any and all real numbers, this must form a subspace. Proof. Well, first of all, any vector in this set S must be of the form a linear combination of these mu vectors. If I was to therefore multiply this by some scalar beta, then because scalar multiplication distributes over vector addition, we have the following. And because scalar multiplication and scalar field multiplication associate, this is equal to the following. Oh, it's still a linear combination of the mu vectors. But because it's a linear combination of the mu vectors, it must have been in the original set S itself. Similarly, if I have any two vectors in this set S, they must both be linear combinations of these m vectors. And with a little bit of algebra, we see that the result must still be a linear combination of these m vectors. Therefore, this set S, that is, all linear combinations of any finite subset of vectors within a vector space, must form a subspace of the vector space V. Claim: for all finite dimensional vector spaces R to the n and C to the n, the only subspaces are either just the zero vector, that is the trivial subspace, or all linear combinations of one or more non-zero vectors. So if you have a subspace, it must be a linear combination of some subset of vectors, and if you have any subset of non-zero vectors, all linear combinations of those vectors must be a subspace. So first, here's another example. Consider R3. There's of course the subspace containing just the zero vector, and equally well, there's the subspace containing all the vectors in R3, the two trivial subspaces. But also, given any non-zero vector u, all linear combinations of that one vector do form a line through the origin, and that is a subspace of the vector space R3. Also, if two non-zero vectors are not scalar multiples of each other, that is, they are not collinear or on the same line passing through the origin, then all linear combinations of u1 and u2, these two vectors, actually forms a plane through the origin. And so all linear combinations of those two vectors does form a subspace, and that subspace is a plane, and that plane must pass through the origin. These are the only subspaces of R3. Now, if you have any other description of a subset of a vector space, to show it is a vector space, you must show that all scalar multiples of one vector that fits that description must also fit the description of that subset, and the sum of any two vectors that fit the description must continue to fit that description. So we already did this previously when we demonstrated that all polynomials of degree less than or equal to 5 forms a subspace of the vector space of all polynomials in X with real coefficients. Now, there is one nice shortcut. If you notice that the zero vector does not fit the description, you may automatically conclude that the subset is not a subspace. You don't have to show anything else. However, if the zero vector does fit the description, you then have to follow the two above steps to demonstrate that the subset is indeed a subspace. We're going to look at a few additional examples in the next topic. Following this topic, you now understand the idea of a subspace. You know that a subspace must contain the zero vector. You are aware that all subspaces in f to the n are the result of considering all linear combinations of a finite set of vectors. For example, all non-trivial subspaces of R3 include all lines and all planes through the origin. You also know that to prove that a subset is indeed a subspace, you must show it is closed under vector addition and scalar multiplication. However, if you can immediately show that it does not contain the zero vector, you immediately also know that it cannot be a subspace. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!